Not to pat myself on the back, but...
Yeah. Okay. So we're going to do a PID controller demo now. And what I've got running here is I've got LabVIEW running. I've got a VI that has a PID controller in it. So it's measuring the actual angle of this little arm here. Remember how we used that robot arm, one link example several times? Well, that's what we're going to do with this demo. We're going to use a one link connected to a motor with an encoder attached to it, so that the encoder has a feedback signal to our controller that tells it measures the actual angle that we're rotated to. So when I started the VI, I had it at this little angle, so it takes whatever the starting position to be 0. So it's a little bit at a slight angle, but we're in a pretty good shape, I think. So this is just going to be our 0. Like, pretend that that's vertical. Okay, we will. I'll stop it and I'll restart it, because I know that you guys will be disappointed if it's not closer to vertical. Is that close to vertical? I can't really see it.
Yes.
Yeah.
All right. Okay. So now that's our new 0. Okay. Supposedly. Okay. So now this is what's the actual hardware here. So the measurements being taken by the encoder. The MyRio is this little microcontroller here. It's a board. It's a little bit like an Arduino. If those of you are familiar with Arduino, want that as a reference. And the MyRio is where the control all happens. Okay, so it's going to take in the optical encoder's position location information, and it's going to run it through an algorithm that tells it, okay, if the error is this much, I need to put in this much voltage to the motor. Okay, so it's going to control the motor as well. And the motor controller also has a power source, an external power source. The MyRio is not powering the motor. The power actually comes from this DC power supply here. So the DC power supply is supplying the voltage that gets essentially gated to the motor or not. Okay, so I can change the command angle in the VI here. Let's see, it's over on this side. So notice how shaky it is, right? Why is it so shaky? Well, partly it's just me, but part of it is that I've just got a proportional controller running. Okay, so right now I've got a proportional controller running. If I do a step change in the command, that's the response we get. And you can actually see the graph of the measured output here. If you can see in the pink, we have the actual measured position, and in white, we've got the commanded position. So we change the commanded position, and we get this oscillation that happens. So with a proportional controller, this happens a lot. You get this long train of oscillations that occur over a long period of time. So one way to deal with that is to increase the derivative a little bit. I will first do integral though. You might be able to tell that there is some steady state error that is this thing not like tightened in? Some steady state error that happens when we do the proportional controller. It's kind of hard to see on the graph, but it's a few degrees that we're off. So we can increase the integral a little bit, and I have got a knob here for integral gain, so I'll increase that. And what it'll do is it'll actually compensate for the steady state errors over time. Now I'm not doing a full controller design, so I'm not, this isn't a very precise thing. I'm just choosing a gain, I'm just increasing it, just tuning it by hand. But if I move here, hopefully we'll see a steady state error correction. You see just a little bit of one happening here over time. It's pretty slow. We could increase that integral term a little bit, and you can see, okay, that was pretty good. It brought it down to essentially 0 or small. The hardware is a little sticky. Some of the motor is really crappy, so that's part of the problem here, but it's got some backlash in it. So some of that steady state error is due to backlash and not due to the controller. Good. And finally, maybe we want to speed up this response. The response is honestly, it takes quite a while for it to settle down, right? It's pretty slow to respond. So we might want to give a little bit of derivative control in, so include a little bit of derivative in our derivative gain in our controller. So let's see what we get. Wow, a lot quicker to settle down to the steady state value, right? So that's what the derivative gives us in general. It gives us that initial change in the error. It takes the derivative of that and it tries to like go out ahead and say, oh, the derivative or the error just changed drastically positive. So it does a big effort to try to fix that error. So it responds quickly when you increase the derivative error. But notice that this was just ad hoc. I just changed the gain and we saw the performance improve, but we don't know if we're designing it to have a specific settling time. You kind of need to do the calculation with a derivative compensator to really decide where that's going to show up. So that's the demo. Do we have any questions about how to do this? So if you guys are going to be controlling something in your senior design projects next year, for instance, you're going to want to do something like this. Like maybe you're going to control the position of something, or maybe you're going to control the speed of something. You need some measurements of the parameter, and you need also the controller to send a command signal. You need some power to drive a motor, usually a motor. Yeah?
Are you using the DC power supply as an op-amp?
I'm using the DC power supply as the power source for what's actually a pulse width modulation motor driver. So there are these nice single board H-bridge motor drivers, PWM motor drivers that are pretty cheap. I mean, you can get them for like $20 for a single one, but if you order them in mass, you get a lot cheaper price. And what they do is they let you connect a high-powered DC power supply that's not variable to a motor using PWM signals. So you can use your controller, like the MyRio in this case, or the Arduino to put out a PWM signal, which is very easy for it to do. But what's hard for the MyRio or the Arduino to do is to supply any power to the motor. And so you send that PWM signal in, which essentially gates the higher powered DC power supply source. Yeah, and it's pretty robust. There are certain cases where you want to have actually analog amplifiers. We've got some analog amplifiers in the lab too to do some things. So they're not portable really. They're like benchtop analog amplifiers. It's going to be a lot more expensive if you go that route. Any other questions? So this is all digital implementation, right? This is all done in a digital controller here. We could have created this thing using, since PID, we would need to use op amps to create the circuit. But we could create the circuit with an op amp, and we could adjust the gains using. Usually, we'd use a variable resistor in each of these. So you could have 3 knobs that are the P, the I, and the D. So, yeah. Okay, that's all I've got. Did you guys have any questions? Any other questions? Okay. Oh. Okay. Double me. Oh, at an angle. Did we get the MyRio here?
Yeah.
Okay. Awesome. All right, guys.